Now we will talk about a different approach for the interaction between magnetic moments. So this is based on the idea that if you have a localized moment atom, in a localized moment atom, we should really consider only the electronic moments interacting only with their nearest neighbors. The next nearest neighbors will be too far away and the interaction is negligible. So the electronic moments interact only with their nearest neighbors. And in that case, we have to calculate how many nearest neighbors we have. You see one example here. This is a simple cubic structure. So in the simple cubic structure, we have atoms at the corners of a cube. And if you count the number of nearest neighbors, the cube has a side A. The nearest neighbor distance is A. So if you look at this red atom at the corner, you can see that there will be one at the top, one at the bottom, one to the side, one to the right hand side, one to the left hand side, and one will be perpendicular to the page. Those are the ones I call 5 and 6. So the number of nearest neighbors is 6. So we call the number of nearest neighbors is called the coordination number. And if you look at the simple cubic structure, in simple cubic structure, the coordination number, I'm going to show it with Z is equal to 6. If you have an atom in the middle of a cube that is that is bonded to the atoms at the 8 corners, so then you have body-centered cubic structure. In body-centered cubic lattice, we have Z is equal to 8 because we have 8 corners and one atom in the middle. In face-centered cubic structure, Z is equal to 12. And hexagonal closed packed structure, HCP, Z is equal to 12. So this is simple cubic, body-centered cubic, face-centered cubic, and hexagonal closed packed structures. Those are the most common lattice structures that we see. And I'm going to give you a link to a video that you should watch explaining where these structures come from and how to count the coordination numbers. So I've only shown it to you for simple cubic. So if we are neglecting the interactions with the next nearest neighbors, we're only considering the nearest neighbors, we can write in this approximation, we can write the exchange field Hx is going to be given by Hx equals to sum over nearest neighbors Jij Mj. So this is the exchange field that is felt by the ith moment. We count the contribution from all nearest neighbors. And then for all nearest neighbors with the same distances from the moment of interest, if I consider that the coupling constant Jij between all nearest neighbors is J, which is reasonable because we have equidistant atoms from the same atom, so then the exchange field will simplify to J constant sum over nearest neighbors Mj. So if we look at the sign of this coupling constant, if J is positive, we will see ferromagnetic alignment of moments. On the other hand, if this coupling constant J is negative, we will have anti-ferromagnetic alignment, which means they will be pointing in opposite directions. So ferromagnetic alignment forces the moments to point in the same direction. In anti-ferromagnetic alignment, they will be pointing in opposite directions. Now, based on this, if I write the exchange energy will be given by minus mu 0 m dot the exchange field. So it will be m dot exchange field, the magnetic moment of interest. So this will be, since it will be aligned with the exchange field, minus mu 0 m J sum over, this is capital J, sum over nearest neighbors Mj, and because all the nearest neighbors will have the same moment as our own atom, and we're assuming that we have a coordination number Z, this is going to give us, for the exchange energy, minus mu 0, the summation will give us Z terms, coordination number, J coupling constant, times m square, which is magnetic moment per atom. So here I'm assuming I have identical atoms, so identical magnetic moment per atom in the simplest possible case. Okay, so this is assuming the magnitude of m sub I moment is equal to magnitude of m sub j for all I and j. So that means I'm assuming identical atoms. Okay, so before we talked about mean field approximation, where we assumed that the interaction constant, coupling constant Jij is a constant for all moments, and we can take it to be J, and then the exchange field will be sum over all J, Jij, Mj. And based on this, we have reached the conclusion the exchange energy is minus mu 0 gamma Mi dot Ms, the saturation magnetization. Now, with the nearest neighbor interaction approximation, we can say that we should neglect the interaction with the next nearest neighbors. We should only consider nearest neighbors. Then we need the number of nearest neighbors we have. In simple cubic, it's 6, body-centered 8, face-centered 12, hexagonal close-packed structure 12. And in this approximation, the exchange field will be sum over all nearest neighbors, coupling constants J between ith and jth moments Mj, which is forcing it to point in the direction of m sub j if Jij is positive, which is the constant J for all nearest neighbors. And if that's positive, we will have ferromagnetic alignment, negative anti-ferromagnetic alignment. The moment will align with the nearest neighbor moment, or anti-align, which is anti-parallel. So if I write the exchange energy minus mu 0 m dot h exchange, now h exchange is given by sum over nearest neighbors Mj times the coupling constant J. So provided that they point in the same direction, assuming ferromagnetic alignment, for example, J is positive, I would get minus mu 0 Z J m square for exchange energy, provided that the magnetic moment per atom is the same for all atoms. That means I have identical atoms in the lattice.